Hello friends, today we will read about non-aqueous solvents. Most of the chemical reactions are carried out in solution and the behavior of substances also depend upon the nature of solvent. In the earlier days of development of chemistry, the reactions have been carried out only in one solvent, namely water. It has been facilitated by its ready availability. Ease of purification together with its favorable physical and chemical properties such as long liquid range 0 to 100 degrees Celsius, high dielectric constant 78.5, specific heat of volatilization, dipole moment, etc. Water is neutral, odorless, non-toxic and non-poisonous. It can therefore be handled safely. The properties of water make it an excellent and useful solvent for a large variety of substances. In fact, the excellent properties of water have been hindered the development of non-aqueous solvents. The solvents other than water which are used for carrying out chemical reactions are called non-aqueous solvents. Attempts have been made to find out some other substances which could behave as good solvent like water. Organic chemists have been using many solvents such as benzene, carbon tetrachloride, acetone, ether, etc. for dissolving organic compounds which are insoluble in water. Now there are many other solvents available. For example, liquid ammonia, H2SO4, liquid HF, liquid sulfur dioxide, etc., which have been frequently used. In the present unit, we shall discuss briefly the important feature of non-aqueous solvents such as NH3 and SO2. Physical properties of solvents and their role in chemical reactions. The usefulness of a solvent is determined from its some specific properties that may help to carry out the chemical reaction and separate the products more conveniently. Some of the important physical properties of solvents are discussed below. Melting point and boiling point. Liquid range. The melting and boiling point of a solvent determine the temperature range within which the solvent can exist in the liquid state under atmospheric pressure. Since most of the reaction in a solvent system are carried out in liquid phase, the melting point and boiling point give the temperature range within which the solvent is useful. The melting and boiling point for some common solvent are given. Solvent H2O melting point 0.0, boiling point 100. Ammonia का melting point minus 77.7, boiling point minus 33.4. It is clear from above table that water has excellent liquid range 0 to 100 degrees Celsius at ordinary temperature and pressure. Acetic acid can also act as solvent at ordinary temperatures, while ammonia and sulfur dioxide can act as solvent only at low temperatures. Second, heat of fusion and heat of vaporization. The values of heat of fusion and heat of vaporization help to know the nature and strength of forces which hold the molecule of solvent together in the solid or liquid state. As we know, the amount of heat absorbed by 1 mole of a substance to change from solid to liquid state is called its molar heat of fusion. Similarly, the heat absorbed by 1 mole of substance to change from liquid to vapor state is called its molar heat of vaporization. Larger the value of heat of fusion or heat of vaporization, the stronger are the intermolecular binding forces in the solid or the liquid respectively. Therefore, the magnitudes of molar heat of fusion and molar heat of vaporization gives us some insight into the nature and strength of intermolecular forces, and these also determine the solvent properties. A better idea of intermolecular forces in a solvent is obtained by the ratio of molar heat of vaporization to boiling point. The ratio is called Proton constant, that is delta H evaporation upon delta TB, Proton constant. For normal liquids, if molar heat of vaporizations are expressed in Cal and boiling point in absolute scale 0 Kelvin, then the Proton constant has the value 21.5. Such liquids exist as independent molecules without any bond between them. A higher value of Troughton constant indicates associated molecules. For example, common solvent like water, ammonia, hydrogen, fluoride have Troughton constant value greater than 21.5 and are therefore associated liquids. The molecule of these liquids are polar. The association of polar molecules is due to their tendency to orient themselves so that the oppositely charged end of molecules come near to each other. The value of molar heat of fusion for water and ammonia are almost same. This means that the force which hold molecules together in water and ammonia are of same magnitude. Third is dielectric constant. This property is a measure of polar nature of solvent and help to estimate the solubility of polar or non-polar substances in the solvent. According to Coulombic law, the force of attraction between two charged ions is given by F is equal to Q positive Q negative upon ER square. Here Q positive and Q negative are the charges of cation and anion respectively. R is the distance between them equal to the radii of ions. E is a constant called dielectric constant of solvent. If E is large, the force F will be small. As a result, only a small amount of energy will be required to separate the ions and hence it will be easy to dissolve an ionic substance. Thus, in solvents of high dielectric constant, the ionic substance will dissolve radially. With the decrease in dielectric constant, the solubility of ionic compound will decrease. The dielectric constant for some common solvents are given. H2O dielectric constant 81.7 at 18 degrees Celsius. NH3 का dielectric constant 22.0 at minus 33.5 degrees Celsius. SO3 का dielectric constant 17.3 at minus 16 degrees Celsius. CH3 COOH 9.7 at 18 degrees Celsius, etc. It is clear that solvents like HF and H2 are good solvent for ionic and polar compounds because of their high dielectric constant values. On the other hand, solvent like NH3 and SO2 with small values of dielectric constant show decreased tendency to dissolve ionic compounds and especially those containing multi-charged ions. For example, carbonates, sulfates and phosphates are practically insoluble in liquid ammonia or liquid sulfur dioxide. Fourth one is dipole moment. The dipole moment is related to dielectric constant of solvent. An ionizing solvent has large dipole moment and also has a large dielectric constant. It is related to polarity of the bond in the molecule. Greater the polarity of bond in molecule, larger is its dipole moment. Solvent having high dipole moment have greater tendency to dissolve the polar or ionic substances. This is because of the fact that the greater polarity results in strong bond between the solvent and the solute molecules and large solvation energy is released. This large solvation energy is sufficient to overcome the lattice energy in the solute molecules and help in dissolving the solute. Fifth one is viscosity. It is measure of the fluidity of the solvents. Solvents like water, ethyl alcohol, and carbon tetrachloride have low viscosities and are highly fluid and flow rapidly under ordinary temperature. On the other hand, anhydrous sulfuric acid and high molecular weight hydrocarbons have high viscosity and flow at a much lower rate at ordinary conditions. In solvent of low viscosities, the operations such as precipitation, crystallization, filtration, etc. can be easily carried out without any difficulty. With increasing the viscosity of a liquid, increase the difficulty of such operations. Now the types of solvents. Non-aqueous solvents have been classified in many ways. The following are the important classification based upon the chemical properties of solvents. First one is protonic and non-protonic solvents. Second, acidic, basic or amphoteric solvents. Third one is ionizing and non-ionizing solvents. Fourth is coordinating and non-coordinating solvents. Now we will read about protonic and non-protonic solvents. The solvents from which proton H positive ions can be derived are called protonic or protic solvents. Therefore, protonic solvents contain ionizable hydrogen. Common examples are H2O, HF, H2SO4, HCN. The solvents from which protons cannot be ordinarily derived are called non-protonic solvents. These are also called aprotic solvent. In other words, these solvents do not contain ionizable hydrogen atom. Common examples are liquid SO2, N2O4, C6H6, CHCl3, CCl4. Now, second one is acidic, basic, or amphoteric solvents. This classification is based upon the acidic or basic behavior of solvent. The solvent which have a strong tendency to donate protons are acidic in nature and are called acidic solvents or protogenic solvents. For example, H2SO4, liquid hydrogen fluoride, acetic acid. Solvents which have strong tendency to accept proton and are basic in nature are called basic or protophilic solvent. For example, liquid ammonia, pyridine, hydrazine, ethyl diamine. The solvent which neither have a strong tendency to gain nor a strong tendency to lose proton are called amphoteric or amphoteric amphoprotic solvents. In other words, they neither behave as strong acidic nor basic but can behave as a acidic as well as basic depending upon the nature of reacting species. For example, water, ethyl alcohol, methyl alcohol. Now, third one is ionizable and non-ionizable solvent. The solvent which are capable of undergoing self-ionization or auto-ionization are called ionizing solvents. Some common examples are H2O, NH3HF, SO2, N2O4, ClF3, BrF3, POCl3, etc. These solvents are generally polar or ionic in nature. On the other hand, the solvents which do not ionize at all are non-ionizing solvents. Some common examples are benzene C6, carbon tetrachloride CCl4, hydrocarbons, etc. These are non-polar or non-ionic in nature. Now the fourth one is coordinating and non-coordinating solvents. The solvent which are capable of coordinating with the metal ions or anions of solvent solute are called coordinating solvent. For example, NH3SO2 dimethyl sulfoxide. For example, NH3SO2 dimethyl sulfoxide DMSO4 acetonitrile CH3CN. On the other hand, the solvents which are not capable of coordinating with the metal ions or anions of the solute are called non-coordinating solvent. For example, CCl4 saturated hydrocarbons. These are not of much interest to inorganic chemists. Now we will read about the types of reaction in non-aqueous solvents. The following type of reaction commonly occur in non-aqueous solvents. Metathetical or precipitation reactions. The reaction in which precipitation occurs on mixing two solutions are called metathetical or precipitation reaction. These type of reaction can be predicted if the values of the solubility products of compounds formed in the solvent are known. These values depend upon the nature of the solvent used. For example, in water, silver nitrate and barium chloride react to give a precipitate of silver chloride, leaving barium nitrate in the solution. On the other hand, in liquid ammonia, precipitate of silver chloride combines with barium nitrate to give precipitate of barium chloride, leaving silver nitrate in solution. Therefore, reversal of a chemical reaction take place on changing the solvent. Similarly, sodium hydroxide is highly soluble in water, but it can be precipitated in liquid ammonia. Water soluble copper sulfate may be precipitated in anhydrous acetic acid. Second, salt formation. The reaction between appropriate acidic and basic substances to form salt are called salt formation reaction. In such cases, the solvent used must be one in which the appropriate acid and base can exist. For example, sodium uride cannot be prepared by the reaction of urea on sodium hydroxide, in which it is because the strong base available in water will not take a proton from urea molecule. In other words, the sodium salt of urea is unstable in water, and uride ion will take a proton from water to form hydroxide ion. However, this salt can be easily formed in liquid ammonia solution by the reaction of urea with strong base sodamide. Third is acid base reactions. The acid base reactions in non-aqueous solvent can be explained on the basis of solvent system concept. As already learned, according to solvent system concept, an acid is a substance that by direct dissociation or reaction with the solvent gives the cation characteristic of solvent. Similarly, a base is a substance that gives the anion characteristic of solvent. The acid-base behavior of substance depend upon the acid-base nature of solvent, the character of solute, and the solute-solvent interaction. In the case of protonic solvent, cation is solvated proton, and the Bronsted protonic concept is same as the solvent system concept. For example, in liquid ammonia solvent, NH4 positive ion act as acid and NH2 negative ions act as bases. In non-protonic solvents such as benzene, carbon tetrachloride, Lewis acid-base type of reaction can occur because of non-ionization of solvent. The acid-base behavior of substance in a solvent depend upon the acidity or basicity of the solvent. For example, acetic acid behaves as strong acid in ammonia, weak acid in water, but a base in sulfuric acid. Fourth one is solvolytic reaction or solvolysis, the reaction in which the solvent molecule react with the solute in such a way that the solvent molecule split up into two parts, one or both of which get attached to solute molecule or ion are called solvolytic reactions. Since these reactions occur through self-ionization of solvent, the concentrations of either the cation or anion is changed. For example, the solvolytic reaction in water, ammonia, and ethanol. It may be noted that in case of solvent like water, ammonia, alcohol, acetic acid, the terms hydrolysis, ammonialysis, alcoholysis, and acetylysis are used respectively. Fifth one is solvation. The reaction in which the molecule of solvent get attached to solute species, cation, anion, or molecule are called solvation reaction. The species formed is called solvate. The solvation reaction in water, ammonia, alcohol, etc. are called hydration, ammoniation, alcoholation, and the resulting solvent are called hydrates, ammoniates, alcoholates, etc. Solution of a cation occur through an ion dipole interaction between the positive cation and the negative end of the dipole, or through coordinate bond in which the solvent molecule donates a pair of electrons to the cation. On the other hand, solution of an ion occurs through ion dipole interaction between the negative ion and the positive end of solvent dipole, or through hydrogen bonding in case of solvents such as water, ammonia, or hydrogen fluoride. It may be noted that in certain cases it is difficult to distinguish between solvation and solvolysis because in many solvolytic reactions the first step consists of solvation reaction. However, the term solvation is used for those reactions in which the solvent molecules remain in the resulting product. Let us discuss some reactions in two common aqueous solvents.
Liquid ammonia. Liquid ammonia is one of the most extensively studied known aqueous solvent. It is now used as highly useful solvent and a reaction medium for many type of organic and inorganic synthesis. Its most of the physical properties resembles those of water, as given in table 4. फ्रीजिंग पॉइंट अमोनिया का होता है 77.7, वाटर का 0, बॉइलिंग पॉइंट ऑफ अमोनिया -33.38, and of water 100. Density of ammonia 0.68, density of water 1.0. Dielectric constant of ammonia 22.0, and of water is 78.5. Comparison of properties of liquid ammonia and water. The comparison of properties of liquid ammonia and water reveals the following points. First one is liquid range. The melting and boiling point of liquid ammonia are lower than those of water. In liquid ammonia, the liquid range is from -77 to -33 degrees Celsius, and therefore it presents some handling problems. Therefore, some precautions have to be taken while using liquid ammonia as a solvent. It is generally handled in cooled vessels, and nowadays a wide range of techniques have been advanced for handling it. Second is hydrogen bonding. Like liquid ammonia is an associated solvent through hydrogen bonding because it contains a strongly electronegative element nitrogen. However, ammonia molecules are less strongly associated because nitrogen is less electronegative than oxygen, and therefore NH N bond is weaker than OH O bond. As a result, the freezing point and boiling point of ammonia are less. Since ammonia is less associated than water, it is better solvent for organic compounds. Third one is dielectric constant. The dielectric constant for ammonia 22 at -33.5 degree Celsius is lower as compared to water 78.5 at 25 degrees Celsius, suggesting its lesser tendency to dissolve ionic compounds. Liquid ammonia is therefore a poor solvent for ionic substance. Soluble salts include most ammonium salts, nitrates, thiocyanate, and iodides. Fluorides and many oxysalts are generally insoluble. However, ammonia have lower viscosity 0.254 cp at minus 33.5 degrees Celsius than water 0.959 cp at 25 degrees Celsius, and this might be expected to promote greater ionic mobilities and therefore compensate to some extent for the effect of the electric constant. Fourth one is self ionization. Both ammonia and water show comparable self ionization. However, the extent of auto ionization of liquid ammonia is less than that of water. This is clear from its low specific conductance and lower ionic product. Therefore, ammonia can conduct electricity to a feeble extent. Ammonia is a better solvent than water. The following properties of ammonia make it a better solvent than water. First one is liquid ammonia is very poor conductor of electricity. The specific heat of ammonia is more than that of water. Liquid ammonia is less viscous than water. Most salts, when dissolved in liquid ammonia, conduct electric current better than in water. This is not due to ionizing power of ammonia, but due to low viscosity, which greatly increases the mobility of ion. Liquid ammonia has high critical temperature and pressure. It is less associated than water due to lesser hydrogen bonding, and therefore is a better solvent for organic compounds. Liquid ammonia forms strong reducing metal ammonium solutions with alkali metals. Therefore, it is an excellent solvent for many reduction reactions. Reaction in liquid ammonia. As mentioned earlier, ammonia has water-like properties as a solvent. It is therefore expected that the reaction which take place in aqueous solution can also occur in ammonia solution. Some of important chemical reaction occurring in liquid ammonia are given below. Acid-base reactions. Acid-base reaction in liquid ammonia can be easily understood by comparing the reactions in water. According to solvent system concept of acid and bases, the substances producing H3O positive ion in water act as acid, while those producing OH negative ion act as base. Therefore, the substances producing ammonium ions in liquid ammonia behave as acids, while those producing amide ions behave as bases. For example, ammonium salt as ammonium halides, thiocyanates, nitrates are soluble in liquid ammonia and behave as acids. Similarly, imides, nitrites behave as bases in liquid. The commonest base in liquid ammonia is potassium amide, KNH2, which lithium amide, sodium amide, and alkaline earth metal amides have a very low solubility, and therefore KNH2 is the commonest base in liquid NH3. Protolysis certain compound like urea, acetamide, sulfamide, etc., which are incapable of donating proton to water, can radially donate proton to NH3 in liquid ammonia. These reactions are called proteolysis reactions. Hence, these compounds act as acid in liquid ammonia. Acid base neutralization. In aqueous solution, the process of neutralization of a strong acid and a strong base involves the combination of H3O positive from acid and OH negative from base to form practically unionized water. For example, the neutralization of hydrochloric acid and sodium hydroxide may be expressed as HCl plus NaOH gives NaCl plus H2O, or H3O positive plus OH negative gives 2H2O. In a similar way, the neutralization of an acid and a base in liquid ammonia involves the combination of NH4 positive ion from acid and NH2 negative ion from base. NH4Cl acid plus KNH2 base treated with liquid NH3 gives KCl plus 2NH3. There are many examples of amphoteric behavior in liquid ammonia. The compounds that dissolve both in acids and bases are called amphoteric substances. For example, in liquid ammonia, zinc amide shows amphoteric behavior analogous to that of zinc hydroxide in aqueous solution. Thus, acid gives NH4 positive ion and base gives NH2 negative ion in liquid ammonia. These are termed as amino acids and amino bases. Reactions of amino acids. Amino acid is a substance that furnishes NH4 positive ion in liquid ammonia. Ammonium halide, nitrite, or thiocyanate are very soluble in liquid ammonia giving NH4 positive ion, and their concentrated solutions act as amino acids. We know that acid give hydrogen with metal in aqueous solution. In a similar way, the amino acid solution of ammonium salt in liquid NH3 react with alkali and other metal to give hydrogen. A saturated solution of ammonium nitrate in ammonia also dissolve many metal oxides similar to their behavior in aqueous acids. Solutions of ammonium halide in liquid ammonia may be used as acid in the preparation of silane and arsine. Mg2Si plus 4NH4Br treated with liquid ammonia gives NiH4 plus 2 MgBr2 plus 4NH3. Na3As plus 3NH4Br treated with liquid ammonia AsH3 plus 2NaBr plus 3NH3. Reactions of ammonobases. Ammonobases is a substance which in liquid ammonia solution gives NH2 negative ion. The commonest base is potassium amide, which is more soluble than lithium and sodium amides. Metal salt react with ammonobases to give imides and nitrides which get precipitated in liquid ammonia. Precipitation reactions involve double decomposition because of the difference in the solubilities of various substances in water and in liquid ammonia. A large number of precipitation reactions which are not normally possible in water have been reported to occur in liquid ammonia. Similarly, a white precipitate of BaCl2 is produced when solution of silver chloride and barium nitrate in liquid ammonia are brought together. Lithium chloride may be precipitated by the reaction of ammonia chloride and lithium nitrate in liquid ammonia. Iodides and bromides get precipitated when solution of various nitrate and ammonium halide in liquid ammonia are mixed together. Third, many metal sulfides can precipitated in liquid ammonia by ammonium sulfide from the nitride solution of metal. Ammonolysis. The solubilisis reaction in liquid ammonia are called ammonolysis or ammonolytic reaction. These are analogous to hydrolysis reactions and involve the attachment of ammonium ion or amide ion to the reactant. For example, hydrolysis of SiCl4 occurs as SiCl4 plus 4H2O gives SiOH4 silicic acid. Complex formation reaction. Many complex formation reactions in liquid ammonia are reported which are similar to reactions occurring in the aqueous system. For example, zinc nitrate react with potassium amide to form insoluble zinc amide which dissolve in excess of amide due to formation of complex compound of zinc. Formation of ammoniates. Just as water form hydrates, ammonia also form ammoniates with many inorganic salt. In these compounds, the ammonia molecule are coordinated to the cation. Some typical ammoniates are BF3 plus NH3 treated with liquid NH3 gives BF3.NH3 and furthermore examples. Sixth, redox reactions. Liquid ammonia act as an excellent medium for redox reaction. In liquid ammonia, the oxidizing action of strong oxidizing agent is weaker than in water solution. For example, HNO3 in liquid ammonia does not act as an oxidizing agent. Similarly, KMNO4 in liquid ammonia act as a very weak oxidizing agent. On the other hand, reducing agents show increased reactivity. For example, alkali metal act as a very powerful reducing agent in which liquid ammonia, for example, sodium metal in liquid ammonia reduce CuI to Cu, KMNO4 to K2MNO4, etc. Solution in liquid ammonia. The dielectric constant of liquid ammonia is low, therefore it is expected to be a poor solvent for ionic substance. Amongst the inorganic compounds, all ammonium salt, nitrates, thiocyanates, and iodides are soluble in liquid ammonia. Oxides, hydroxides, carbonates, phosphates, sulfates and most of sulfides are insoluble. Most fluorides are insoluble in liquid ammonia, and the solubility among halide increases as F negative is greater than Cl negative, Br negative, I negative. Most of iodides are soluble. Calcium and zinc chloride, which are extremely soluble in water, are quite insoluble in ammonia. Organic compounds such as halogen compound, alcohol, ketone, ester, simple ethers, phenols, amines, nitro compounds, etc. are readily soluble in liquid ammonia. Aromatic hydrocarbon are sparingly soluble. Paraffins and benzene are not soluble. Amongst the elements like Mg, magnesium, aluminium, zinc, calcium, LaCe, Mn, etc. are only slightly soluble in liquid ammonia. Alkali metal or alkaline earth metal are highly soluble in liquid ammonia. These form very interesting solutions and are discussed below. Non-metal like PISE are soluble in liquid ammonia. Solution of alkali metal in liquid ammonia. The most striking property of liquid ammonia is its ability to dissolve alkali metal. The resulting solution are blue and extremely good electrical conductors. The important characteristic of alkali metal solution are these are blue in color and the color is independent of metal dissolved. Second, when the concentration of metal is increased, the color changes to bronze and shows metallic appearance. Third, these solutions are conducting and show strong reducing properties. Fourth, these solutions are paramagnetic and the paramagnetic character decreases with increasing concentration. If the reagents are pure and dry, sodium solution in liquid ammonia are stable and can be preserved for several days. When alkali metals are dissolved in liquid ammonia, they ionize to give metal ion and valence electrons. The important application of alkali metal solution in organic chemistry is the reduction of many functional groups and unsaturated compound. As already studied, the liquid ammonia is a thoroughly studied non-aqueous solvent. Some of its advantages and disadvantages as a solvent are given below. Advantages of liquid ammonia as a solvent: the dissolution of alkali metal without chemical reaction is one of the greatest advantages of using liquid ammonia as a solvent. The dissolved alkali metals can be recovered from the solution by evaporation. The alkali metal solution are strong reducing agents, even stronger than hydrogen. Ammonium salts dissolved in liquid ammonia act as amino acid, and these find applications in preservative chemistry. They can be used to prepare silane, arsine, etc. The tendency for solubilisis is less in liquid ammonia than in water. Now, the disadvantages of liquid ammonia as a solvent. The liquid range for liquid ammonia is from minus 33.3 degree to 77.7 degrees Celsius. Therefore, a low temperature or high pressure is necessary while working with liquid ammonia. Liquid ammonia has an offensive odor, therefore, it requires special technique to use it as a solvent and as a reaction medium. Liquid ammonia is a hygroscopic in nature, hence, all the reactions are to be carried out in sealed tubes. Liquid sulfur dioxide. Liquid sulfur dioxide is a non-protonic solvent or aprotic solvent because it does not contain any hydrogen atom. It is also one of important non-aqueous solvent and has been widely used in industry. Under normal condition of temperature and pressure, sulfur dioxide is a gas, but it can be readily liquefied and is easily maintained in the liquid phase if it has a wide liquid range and can be used as a solvent. It can be easily purified by passing the gas through sulfuric acid and through P2O5 to remove traces of water. Its dielectric constant is small and therefore is a good solvent for covalent compound. The characteristic physical properties of liquid sulfur dioxide are given in table second. Freezing point minus 75.46, boiling point minus 10.02, density 1.46, viscosity 0.428, dielectric constant 17.4, dipole moment 1.61, specific conductance 4 into 10 की power minus 8 at 10 degrees Celsius. Structure of sulfur dioxide molecule. Electron diffraction studies have been shown that sulfur dioxide in a gaseous phase has the angular structure. The valence the valence bond theory predicts that the SO2 molecule is a resonance hybrid. Autonization of SO2. Pure SO2 is a poor conductor of electricity, though it is believed to ionize as 2SO2 gives SO2 positive, SO2 positive plus SO3 2 negative. The thionyl ion is analogous to hydronium ion and ammonium ion, and sulfate ion correspond to hydroxyl and amide ion of aqueous and ammonia system respectively. Reaction in liquid sulfur dioxide. Some important chemical reaction in liquid sulfur dioxide are discussed below. Acid base reactions. Liquid SO2 undergoes autoionization as 2SO2 gives SO2 positive plus SO 2 negative. According to solvent system concept of acid and bases, the compound which gives thionyl ions in solution of SO2 would behave as acid, whereas compound giving sulfite ion in liquid SO2 would act as bases. For example, compounds such as SOCl2, SOBr2, etc. act as acid in liquid SO2. Solvolytic reaction in liquid sulfur dioxide are not as common as they are in other protic solvents such as NH3. Some reactions are given below. Ammonium acetate is solubilized in liquid SO2. This reaction is analogous to reaction of ammonium acetate in water. Certain covalent halides such as PCl5, PBr5, UCl6, ASCl5, WCl6 undergo solubilisis in liquid SO2 in sealed tubes. Many binary halides such as SbCl3, SbCl5, SiCl4, SnCl4, VCl3, SCl2, SCl4, MoCl6, etc. do not undergo solubilisis in liquid sulfur dioxide. The formation of solvates, that is the addition of compound with solvent, is also known. Typical example of solvates are NaI.4SO4 RBI.4SO2, KBr.4SO2. Third one is precipitation reaction. A large number of precipitation reactions can be carried out in liquid sulfur dioxide due to selective solubilities of compound. The precipitation of several insoluble compound in liquid sulfur dioxide can be carried out by treating them with soluble compound in sulfur dioxide. Some of these reactions are SbCl3 plus 3 LiI treated with liquid SO2 gives SbI3 plus 3 LiCl. Fourth one is complex formation reaction. A large number of complex ion formation in liquid sulfur dioxide have been reported. For example, the solubility of iodine in liquid sulfur dioxide is greatly increased by the addition of potassium or rubidium iodide. This is due to formation of complex Ki3 or RbI3. Similarly, the increase in solubility of cadmium iodide and mercuric iodide in liquid sulfur dioxide is attributed to formation of complexes. AlCl3 reacts with SO3 2 negative ions to form a precipitate of Al2SO33, which redissolves in excess of SO3 2 negative ions, forming the complex ion AlSO3 3 negative. Organic reactions. A large number of organic reactions have been carried out in liquid sulfur dioxide because organic compounds are soluble in it and it is a relatively inert solvent. Sulfur dioxide of crystallization. These reactions are also called solvation reaction, like water and ammonia salt having sulfur dioxide of crystallization have also been observed. Some examples are NaI.4SO2. These are formed with the highly soluble salt are called analogous to hydrates. Redox reaction. Though gaseous sulfur dioxide behave both as oxidizing and as reducing as in liquid sulfur dioxide does not show any marked reducing or oxidizing tendency. It simply act as a medium for certain redox reaction. For example, iodine is liberated from Ki in the presence of SbCl5 in liquid sulfur dioxide. Some special feature of liquid SO2 as a solvent. Liquid sulfur dioxide possesses some special advantages over other solvent as a reaction medium. Some of these are: it has low boiling point and this allows its easy evaporation and therefore removal from the reaction mixture. It has low melting and therefore allows reaction to be carried out at low temperature. Liquid SO2 is an inert solvent. It has unusual solvating power for both covalent and electrovalent compound. It is a better medium for covalent compound like hydrocarbon and is used for the purification of some petroleum products. It is used as a diluent for the superacid medium, which help in reducing its viscosity without affecting its acidity. Thank you.